Hey, I'm Liam, and this is a homemade robot arm that I built. To start off this video, I'll give a quick demonstration of it in action, and then I'll go into a bit of explaining how I built it. So, let's go ahead and start the robot. It's going to pause for a little bit, and then we're going to see that it's going to move in between some coordinates. So, every position that it's at right now is a coordinate in 3D space that it's moving to. And it's using an inverse kinematics algorithm to be able to move in between these points smoothly and fluidly. This servo on the very end is a bit dead, so it's a bit underpowered. So it does jitter a little bit, but mostly this is completely functional. Once the robot has finished moving through its set waypoints, it will eventually stop, and it will then be usable by user control. So it's entered that phase now, and I can go ahead and move it using my computer however I'd like. So here I'm going to set the bottom pivot to look straight ahead. You can see that it moves. Okay, here let's take a look at how the gripper on the robot works. So I can control the gripper from my computer. So I'll go ahead and close the gripper, and you can see that the jaws come together, and then I can open the gripper like this. So let's move the whole thing down so that we can try to pick up something. So we'll try this. Maybe a little bit lower. Too low. So we can put a roll of tape here as an example, and then we can close the gripper from the computer, and it will close on the roll of tape, and then we can move up the rest of the arm, picking up the roll of tape, and we can now put it anywhere. Okay, so after the demonstration, I now want to talk a little bit about how the robot works and how I went about making it. So to start off with making the robot, I chose to mathematically model the robot by modeling the coordinates of the end effector in terms of the angles and lengths of each segment. I came up with these formulas shown on screen for the x and y coordinate of the end effector based on the angles and lengths, and while I won't go into an explanation for them here, I do have a video linked in the description that goes through the full derivation of these formulas. Now, using these formulas, it's possible to go through each angle and try to approximate to find angles that fit well with the given circumstances and get close to the right coordinate, but there's no explicit solution possible. These formulas are mostly used for checking to see if other solutions to the inverse kinematics, which is the problem of finding angles for a given end effector position, are accurate, because giving a set of angles, you will always get the exact position that the arm will be located at. To actually find the angles, I use an algorithm called Fabric. Let's talk a little bit about how Fabric works, which is forward and backward reaching inverse kinematics. Fabric starts with a model arm. Here I'm going to use 2 segments and 3 points because it's easier to demonstrate. However, you can have as many segments and points as you want, and this works in any dimension of space. How Fabric works is it starts by taking the lengths between each point and the points information themselves. You set a target point and you have an origin point. Once you've given Fabric these input conditions, it begins its first step. Its first step is to move the final point in the linkage to the target point and draw a line from this new location of the final point to the second last point. On the second step, it takes the original length between the second last point and the last point, and it moves the second last point that length along the imaginary line from the target, or now the final point. It also draws a new imaginary line from the second last point to the third last point, which in this case is the initial point. On the next step, the initial point, or the third last point, is moved to the original length between the second and first point away from the second point. And this is the forwards reaching part of the inverse kinematics solver. However, there's an obvious problem here because it's not really any good if the origin moves, because the base of the robot arm has to stay stationary. What Fabric does to solve this is it repeats the process in the other direction. So it starts by moving the first point back to the origin, draws another imaginary line to the second point, moves the second point the length of the first segment along that line, draws a new line to the last point, and moves the last point the length of the second segment along that new imaginary line. That was very fast, but that is the exact same as the forwards reaching process, just going the other direction, which is the backwards reaching part of fabric. Fabric gives coordinates of joints, but it does not give angles of joints like the model we came up with earlier, and it is necessary because the servos need to be moved to angles. We can't just tell them to go to coordinates. However, with the coordinate information of each joint, we can compute the angles using these equations that I've shown on screen. The first equation is quite simple and straightforward. The other two are simply renditions of cosine law that solve for the angles. Here's what the output of fabric looks like in Desmos. You can see that in this 3D view, you have points that go along a 2D plane and reach out to the target coordinate. I also have a 2D version of this Desmos graph that uses the earlier formulas with the sine and cos to solve for the x and y coordinates given a set of angles. This is useful to check to see if our x and y coordinates algorithms and equations actually work. The final thing I wanted to talk about was a bit of the design of the robot. Most of the design is pretty simple and prioritizes minimal complexity in mechanical design. However, the gripper is one exception. The gripper mechanism is shown on screen right now. The servo, which you saw earlier on the gripper, is used to turn this gear in the middle, and this gear is part of a rack and pinion system. When this gear turns, the gripper fingers move towards the middle, and when it turns the other direction, they move away from the middle. I'm quite proud of this design as I had to fit a lot of stuff in a small enclosure. For example, the fingers get in the way of each other as they try and move past the middle point. One final thing I wanted to show was a processing sketch that I developed, which can animate arm movements from one point to another in 2D space. One thing to note is that this model does not use fabric or the earlier method I mentioned, but it actually uses a method where I can strain the second segment of the arm to always be parallel with the imaginary line from the origin to the target coordinate. This means that while I could not explicitly solve for an angle, I could approximate a single angle to very close precision, and from there use that angle to solve for the other angles, which results in this smooth motion where one frame looks very similar to the next frame. This is different than the screen recording I have of using the original formulas of just the sine and cos, because with those formulas you find the most accurate single integer angle that for each angle that will allow you to move the end effector closest to the target coordinate. This is because it's simply not feasible to check every single angle to decimal accuracy. You would quickly have millions and millions and millions of computations. With this method where I solve for just C and constrain the second segment to be parallel, I still have my full range of motion, but I can also solve the equation in only about 1,000 calculations. This is pretty on par with fabric. However, the calculations are much more complex. For example, this is the formula that is used to solve for the angle C. That's about it. I'd like to thank you for watching, and I hope you enjoyed.